Okay, so can you guys see my screen now? Hello? Okay, great.
Yes, sir.
So for today's meeting, we'll finish the remaining modules. So the module 5 and then the module 6. And then as you guys can see for the module 5, we only have 14 slides. So this will only take quick discussion or quick meeting. Okay, so without a further delay, let's start with the definition of a superposition theorem. So superposition theorem is one of the strokes of genius that takes a complex subject and simplifies it in a way that makes perfect sense. So this is another theorem wherein, of course, it will give us an option if we're going to use this one in this particular circuit. So this one is similar with the Kirchhoff's law, Maxwell theorem. Okay, so they have their own edge, they have their own advantages and disadvantages. So the edge of superposition theorem is this one is perfect if we have a lot of sources. So if we have two, three, four, or five, so this one is super useful. Okay, like this one is the most uh, proper theorem that you can use when it comes to multiple sources. Okay, so the strategy used in superposition theorem is to eliminate all but one source of power within a network at a time. So if you have five sources, so you're going to have five combinations separately. Okay, so yeah, this one is time consuming. So having let's say five sources, you're going to have five individual, say, uh, individual currents for that, and then individual voltage drops for that. And then all in all, you're going to combine them. So, ganun kadaming set. So, 5 voltage sources. So, 5 set also. Okay, so later on, you will see on how time consuming this term is. But this one is super useful, again, if you have those kind of scenarios. Okay. So using SIPs or parallel analysis to determine voltage drops and or currents within the modified network for each power source separately. Then once voltage drops and or currents are have been determined for each power source working separately, the values are all superimposed on top of each other, added algebraically to find the actual voltage drops currents with all sources active. So after solving everything, after having all the individual currents, all the individual voltage drops, so you can now combine those individual sets that you have just solved. So once you have combined them, we call that one superimpose. Okay, so you can add them algebraically. So depending on the flow of current, depending on the polarity. Okay. All right. So without a further delay, let's have this example. So as you guys can see, we have the same example like what we have used in Maxwell theorem. So we have 28 volts right here, 4 2 ohms, 1 ohm, and then 7 volts right here. So superposition theorem is applicable since we have two voltage source. Okay. So again, just like what I've mentioned a while ago, when we say uh, voltage source or current source, all you need to do is eliminate all but retain one source. Okay, so if you have two voltage source, then retain one and then eliminate the other one. Okay, and then solve that one for now, and then after solving everything, then you can now eliminate this one and then retain the other one. Okay, so basically whatever you did on the first one, so you have to do that one on the second set. Okay, so for now we'll choose to solve for the left side part. So as you guys can see, we have eliminated or we have shorted the 7 volts right here. Okay, and then retaining the R1, R2, and R3, and then we now only have one voltage source. So as you guys can see, this one is super simple to solve as long as you know the basics of Ohm's law. Okay, so you can now find the total current right here, the total resistance, and then after that you can now find the individual currents, and then you can now find the individual voltage drops. So to do that one, okay, so we have this concept first. So if it's a voltage source, you have to short the that voltage source right here. But if it's a current, okay, you have to leave it open. So in other words, we call that one break. Okay, short is also I know we also have other terminology for this one like make, but mostly we call that one short. Okay, and then break is like an open circuit. Okay, so since we have voltage source on the right side, the 7 volts right here, all we need to do is short it to eliminate that uh, source that you have in there. Okay, so yeah, that's how we do things in here. Then after that, you can now apply Ohm's law. And then here's the result after solving for the Ohm's law. But of course, for you to be able to get this one, let's have our own solution. Okay, because the solution was not shown in here. It's the answer right away. So again, let's do this one using the paint. So we have to find here, find let's say I total, R total. So V total is already given, which is the 28 volts. So we can also find here the I1, I2, and then the I2, and then the I3. We can also find, of course, the voltage drop across R1, and then the voltage drop across R2, and then the voltage drop across R3. Okay, so those are the things that we need to find. Okay, so first we can start with, the R total, since that's one of the easiest way that we can do for now. So to do that one, okay, so again, in R total, we have this formula. Okay, R total is equal to V total divided by I total. Okay, so V total, we already know that it's 28 volts, but we don't know the I total. So in order for us to get the R total, well, we can combine these two, since as we all know, they are in parallel with each other. So 2 ohms, 4 ohms. Let me just check if it's this one. 2 ohms plus 4 ohms. 2 ohms. My bad. So in here, the one that is in parallel is the R2 and R3. Okay, because in here, after combining them, then this one is now is in series with R1. Okay, so my bad on that one. So it's not R1 parallel to R2, but it's R2 parallel to R3. So how will you know if it's, this one is correct? Okay, so wherever is a voltage source, so you should try to eliminate the, let's say, the right side first going to left. Okay, so that's the pattern. So if you have the sources on the left side, so you have to eliminate or simplify the right side going to the left. Okay, so same scenario if you have the voltage source right here. So you have to eliminate the left side going to the right. So in that case, the parallel connection now is the R1 and then the R2. But since we have the voltage source in here, then the parallel connection right here is the R2 and then R3. Okay, so in here, R total is equal to R1 plus whatever is the result of R2 parallel to R3. Okay, and in here, for us to be able to get the uh, parallel of R2 and R3, so we have to use the rules of parallel law. Okay, so in here we have R2 times R3 divided by R2 plus R3. Okay, and in here R2 is 2 ohms, and then R3 is 1 ohm divided by 2 plus 1. Okay, then in here, just by simplifying this one, we'll get 2 times 1 is 2, and then 2 plus 1 is 3. So R2 parallel to R3, 2 divided by 3 is equal to 0.66, I guess. 2 divided by 3 is 0.66667, or you could just simply write here 0.67. Okay, so were you guys able to follow up to this point so far? And how did we solve the value of this one, R2 parallel to R3?
Yes, sir.
Okay, good. So now we can write this one now. Okay, let me have another copy. Okay, but let me just make this one smaller. And let me remove this one, and remove this one, and that one. So this one now is R2 parallel to R3. Okay, and the value of this one is 0.67 ohms. So in here, we can now add the R1 parallel or plus the value of this one, the R2 parallel to R3. So in here, we can now get this one again. This RT is equal to R1 plus R2 parallel to R3, wherein RT is equal to, so R1 is 4 ohms plus 0.67. So RT is equal to 4.67. Okay, so clear on how did we get this R total right here? Okay, so this one is super simple anyway. Then after that, you can now solve for the I total. Okay, so I total is equal to V total divided by, let me use the capital one for consistency. V total divided by R total. Okay, wherein of course V total is equal to 28 volts, and then R total is equal to 4.67. Okay, so in here we could write that I total is equal to 28 divided by 4.67. 8 divided by 4.67. So it will give us a value of, tama ba, ITBT divided by total. Yeah, 4.67. So it will give us a value of 5.95 or 5.96 ampere. So please check also if I or if we have the same result. Okay, verify my answer. Okay, so that just in case that I did put here an incorrect answer or incorrect result, so that we can correct it right away. Okay, so that's the I total. So from here we could already say that I1, okay, is equal to I total, since that is the current that is flowing on our R1. Okay, and then at this point, let's say, let's just call this one node A. Okay, so the current will be split into two. So some current will go here, and then some current will flow in here. Okay, so are we still clear so far?
Yes, sir.
All right. And then from here, we can now solve for the voltage drop across R1, since we already know the value of I1. Okay, so to do that one, so V1 is equal to, or VR1 is equal to I1 times R1. Okay, so we already know that I1 is equal to I total, which is 5.96, but I think the one that we've used in here is 6. Okay, so that's what's bothering me, why we've got 5.96. Anyway, to make this one, as the same as possible, let's just equal this one or equate this one, okay, round up to 6 ampere. Okay, but when it comes to super exact answer, the correct answer is 5.96. But to make it the same with what we have in here, okay, so let's just use 6 ampere. All right, so let me remove this one, and then let's use 6 ampere. Okay, so that we can arrive with the same result as what we have in our module right here. Okay, so let me just align this one. So 6 ampere times R1 is 4 ohms. Okay, so this will give us a result of 24 volts. Okay, so are we clear for the voltage drop across R1? So IT is checked, RT is checked, I1 is checked, and then VR1 is also checked. Okay. So as you guys can see right here, if we have a voltage drop of 24 volts, so we can now have a potential voltage at letter A at exactly 28 minus 24, which is equal to 4 volts. Okay, so to do that one, let me just write here the solution. Let's say potential voltage at VA. So what is now the voltage that will flow on the R2 and R3? So that is the voltage that will remain, or that will be, let's say, that will retain after passing through this R1 right here. Okay, so it's B1. okay, minus VR1. So in here, we have B1 is equal to 28 minus, punta tuloy sa baba. Anyway, let me just remove this one. 28 minus 24 volts, okay, which is equal to 4 volts. Okay, so VA is equal to 4 volts. All right. So are you guys able to follow? And how did we get this 4 volts right here? Okay, so the reason why I did solve, or I did get the potential voltage at node A, since as you guys can see, R2 and R3 is in parallel with each other. So if we have a parallel connection, if we are going to solve for the voltage drop across R2 and R3, we could just simply say that, we only have one single voltage since they are in parallel. So going back to our rule before, as you may still recall, so if they are in parallel, they have the same value of voltage. So in here, we could assume that, okay, VR2 is equal to VR3, wherein the voltage that is flowing in there is equal to voltage A, or the potential voltage at node A. So VA is equal to 4 volts. So voila, we now have the values of VR2 and VR3 right away. Okay, so even though we haven't solved for the value of I2 and I3, so we can already solve for the voltage drop just by analyzing this one, okay, already, since they are in parallel. Okay, well, you can still, do the old method, like, VR2 is equal to I2 times R2. Well, that is only if you know the value of I2, but since we don't know the value of I2 yet, so this one is the best way to determine what is the voltage across R2 and R3. Okay, all right, so are we clear for the VR2 and VR3? Okay, so we now have everything aside from I2 and I3. So solving for the I2 and I3 is now super easy, since we now know the value of VR2, okay, divided by R2. Okay, so VR2 is equal to 4 volts divided by 2 ohms, which is the value of R2. So 4 divided by 2 is equal to, okay, 2 ampere. Okay, so that is now the value of our uh, current across R2. Okay, so the same concept with the I3. I is equal to V divided by R, or I3 is equal to VR3 divided by R3. Okay, so in here we have still 4 volts, since VR3 is equal to VR3 divided by 1 ohms. So in here we have 4 ampere. Okay, so are we clear so far on how did we solve for those individual currents and then individual uh, voltage drops? What about the others? Okay, so this one is mostly, with the help of Ohm's law. So that's why Ohm's law is the fundamentals of everything. Okay, if you know Ohm's law, you can pretty much solve everything. Okay, and then the theorems are just the helper. Okay, on how to simplify this, uh, complex circuit into a uh, simple or simpler circuit. So in here we can now compare this one. Let's try to compare this one with our answers. So let's start with here first. So here are the voltage. Okay, so here's the total voltage, the voltage across R2 and R3, the voltage across R3 and R2. Okay, and then the voltage across R1. Okay, and then for the current, we have the total current as 6 amps, and then the current across R2 and R3, and then the current across R3, current across R2, and then current across R1. And then for the values of our resistors, so we have a total resistance of 4.667 or 4.67, and then we have here a do we have this one 0.667? Yeah, so we have here the parallel value of R2 and R3, which is 0.67. So in my case, I did only get the two decimals. And then here are now the individual resistance. So 4 ohms, 2 ohms, and then 1 ohm for the R3. Okay. And then if you are going to compare, so I think all of our answers are the same with this one. So I total is 6 ohms. R total is 4.67, and then V total is of course 28. And then here are the voltage, okay, across R2 and R3, which is, where is that one? I think we don't have this one, but knowing that they are in parallel, so we have the same value as the R2 and R3, which is 4 volts. Okay, right here. VR2 is equal to VR3 is equal to VA, which is equal to 4 volts. Okay, and then here are the individual voltages. Okay, for VR2 and VR3. And then the 24 volts. Okay, right here for the VR1. Okay, and then the individual currents. So please recheck. And then please let me know if there is a part that you are confused. And please give me a thumbs up once you're done in analyzing and then comparing our answers right here. So at first, if you're not that, familiar with this kind of table, so maybe you'll get shocked and then you'll get confused at first. But once you know understand this one by one, what is this ER1, ER2, ER3, IR1, IR2, IR3. So you will already identify that, this is the current across R2. This is the current across R3. This is the I total, okay, and so on and so forth. Okay, so, okay, just wait a second. All right, so are we clear, guys? Are you guys able to follow?
Yes, sir. Na-follow naman po.
Okay, great. So that's it for the first set. Okay, so we still have the second set, which is the 7 volts on the right side. So let's move on right here. And then here's now the computed values for the second set. So as usual, we're going to have our our own solution for this one, and then we'll compare our answer later on. So in here, the same unknowns. So we have to find the I total. So B total is already given. So I1, I2, I3, BR1, BR2, and then BR3. Okay. All right. So in here, again, we need to find the I total or the R total. So I drop those two. But in here, the easiest way for us to be able to find the I total is find the R total first. So to do that one, we have to simplify this one wherein R1 is in parallel with R2 plus R3. Okay, since after solving the this one, we are now in series with R3. Okay, so with this one, we have to find the value of R1 parallel to R2 first. So this one is R1 times R2 divided by R1 plus R2. Okay, and then let me just copy this one. So R1 is equal to 4 ohms, and then R2 is 2 ohms, and then R1 is 4, and then R2 is 2. Okay. And then in here, we have 4 times 2 is 8, divided by 4 plus 2 is 6. So R1 parallel to R2 is 8 divided by 6. 8 divided by 6 is equal to 1.33. Parang may mali. 4 times 2, 4 plus 2, 6. 1.33. So let me just verify. Ah, yeah, that's correct. So 1.33. Okay, so this is now the computed value for the R1 parallel to R2. So are we clear so far on how did we get the R1 parallel to R2 value? Okay. What about the others? Were you guys able to follow? Okay, great. So again, let me just remove this one since this one now is equal to R1 parallel to R2, which is equal to 1.33 ohms. Okay. And as you guys can see, we can now add the value of R1 parallel to R2 plus the R3. So copy this one and paste it right here. So R1 parallel to R2 is 1.33 ohms, and then R3 is 1 ohm. So RT is equal to 2.33 ohms. Okay. So we now have the value of R total. So after having the R total, we can now solve for the I total. So IT is equal to VT divided by R total. So VT is equal to 7 volts divided by R total is 2.33 ohms. 7 divided by 2.33 will give us a result of 3 is equal to 3 ampere. Okay, so are we clear on how did we get this 3 ampere right here?
Yes, sir.
Okay, great. So again, just let me know right away if you're confused or if you wasn't able to get this one. And then as you guys can see, since we have the current that is flowing from here to there, okay, and then as we all know that's the I total, okay, we could already say that this is already your I3, okay, it's equal to I3. So in here, I3 is equal to 3 ampere, okay. And since we already have the I3, we can now solve for the voltage drop across R3, okay, which is I3 times R3, okay. And then in here, I3 is equal to 3 amps multiplied to R3, which is 1 ohm. So VR3 is equal to 3 volts. So that is the voltage drop. That is the voltage drop across R3, okay. And then the same concept with whatever we have a while ago. So we need to find the potential voltage at this node. So again, let's just name that one potential voltage at node A. VA is equal to VB2, okay, or the B2 itself, minus VR3, okay, the voltage drop across R3. So B2 is 7 volts minus VR3, which is 3 volts. So 7 minus 3 is 4 volts. So that is the potential voltage across node A. Okay, which is, I think it's the same, yeah, 4 volts. And then again, it's the same concept since we have a parallel connection of R1 and R2. So we could say that VR1 is equal to VR2 is equal to VA, which is actually equal to 4 volts. Okay, so can you guys follow so far?
Yes, sir.
Okay, what about the others? All right, so great. So I hope to those who are not giving me thumbs up, we're also able to follow this one. Okay. So from here we can now solve for the individual values of the R1 and R2 since we already have the I3 and then the I total. Okay. So for the I1, okay, we need to have the VR1 divided by R1. Okay. So VR1 is equal to 4 volts divided by R1, which is 4 ohms. So 4 divided by 4 is equal to 1 ampere. And then I2 is equal to VR2 divided by R2, which is equal to 4 volts divided by R2 is 2 ohms. So to give us a value of 2 ampere. Okay. So voila, we now have everything. I total, R total, VR1, VR2 and VR3, and then the I1 and I2. Okay. So again, let's try to compare. Okay. So right now, I like you guys to verify it yourself. Okay, so again, we read this one as ER1, ER2, ER3, ER1 parallel to R2, E total, and so on and so forth. So IR1, IR2, IR3. Okay, so please verify if we have the same result. So, are they the same? Okay, very good, Miss Maris. Very good, Miss Linoran. Very good, Mr. Donato. Very good, Mr. Mabasa. Ah, Maaba, not Mabasa. So, what about the others? Okay, very good, Mr. Gonzalez. Okay, very good, Miss Nicole. Okay, so since we don't have enough time anymore, so very good, Mr. Alburo, we'll just continue the rest on the part 2. Okay, so as usual, goodbye for now, and then see you guys later on the part 2.